Good day, everyone. Welcome back. Hey, today we're going to work a little bit with power series and calculus, meaning derivatives and integrals. So what we're going to take a power series that we already know, and we'll create a new one by either finding its derivative or finding its antiderivative. All right, well, here we go. First, a couple of things to read here. Essentially, what the theorem today, the two parts say, is suppose we have a power series. Remember the way you want to think of a power series is just a really long, infinitely long polynomial that will be a convergent series depending on the value of x. That makes the interval of convergence. And what this says essentially is in part one, if we find the derivative, if we want to find a power series for the derivative, we can just find the derivatives term by term of the terms of the power series. So notice what's being written right here that I'm kind of putting my arrow around. In fact, I'll just use the pen for a minute to circle the general term of this derivative. Now compare it to the general term of your power series up there, remembering that c sub k is really just a constant coefficient. The variable is x, and then the power on each term is the number k, which is also for each term a constant. And so all you're seeing down here is essentially the power rule for derivatives. Remember, the k, the power, comes down to multiply it into the coefficient, and then the power of x, in this case, the power of x minus a decreases by 1. So really all you're seeing here is the power rule for derivatives applied to the terms of the power series. And then here in part two, as you're seeing, is the power rule for integrals. You are upping the power of x minus a by 1 to k plus 1, and then you are dividing by k plus 1, and of course still multiplying by the original coefficient. So all you're seeing right here essentially is you're seeing the power rule for derivatives or for integrals. One little note here about intervals and radius of convergence. If you integrate or differentiate a power series, that should not change the radius of convergence. However, what you might find is maybe a power series that didn't converge at the endpoints before might converge at the endpoints now, and vice versa. Maybe it didn't converge at the endpoints and now it does. So you're going to want to recheck the endpoints of the interval of convergence after integrating or differentiating. We'll get into that shortly. So our first task today is to find the derivative of this function 1 over 1 minus x and express it as a power series. Notice this is the geometric power series, the standard one we were working on in Monday's lessons. The function 1 over 1 minus x can be expressed as the power series or the polynomial 1 plus x squared plus x cubed and on. That's the standard geometric power series. Now what we're asked to do is find this derivative of this series and note what it's the derivative of, or what it's the power series of. Now we can just do this by taking that equation that the function, let's change this to a color you can read, function f of x is 1 over 1 minus x, and its power series, I'm just going to write it out this way, 1 plus x squared dot 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 general term x to the k, when the interval of convergence for this one is x between negative 1 and 1. Now we're going to express the derivative. Okay, so let's make the next line f prime of x. And if I remember that the original thing can be written 1 minus x to the minus 1, that makes it easy to find this derivative. It's going to be negative 1 times 1 minus x to the minus 2. And then don't forget the chain rule. We got to multiply by minus 1 again. So the new function we're finding the power series for is this one. It'll be positive 1 over minus x squared. Now, on the other hand, we'll just go term by term and find the derivative of this power series. Well, the derivative of the 1 will be 0, and then I'll have the derivative of x, the derivative of x squared. I didn't write the x cubed, but I'll write the derivative of x cubed, it's 3x squared. So that way the general term, I can just find the derivative of x to the k, and that's just really just using the general power rule. Bring k down, and now the power of x is k minus 1. So now I'll notice that in this derivative, the term that was previously the k equals 0 term is no longer there. This 1 is associated with k equals 1. So when I write the compact version of this power series, the k now starts at 1, and it's going to be k x to the k minus 1 for the general term. Notice that does have the series start at the number 1. Okay, because when k equals 1, the first term will be 1 times x to the 0. And then the second term will be 2 times x to the 1. So this does work. And so our combo goes like this. The derivative of the function 1 over 1 minus x would be written with normal differentiation of that, 1 over 1 minus x quantity squared. By differentiating the power series of that original function, here's the power series for the derivative right there. Part B of this problem is to take that geometric power series one more time, the one for 1 over 1 minus x, and this time we're going to integrate to find a new power series and express and find out what it's the power series for. Okay, well, if f of x is 1 over 1 minus x, and in power series form, it's 1 plus x cubed, like that, x to the k, general is the general term. We're now going to integrate this. So on the one hand, we're just integrating 1 over 1 minus x. But on this side, we're integrating this power series, the polynomial 1 plus x. We'll stick in the general term too. Okay, so on the left side, to find out what function this new power series is representing, let's just integrate this the usual way. You might want to think in terms of a u substitution. U could be 1 minus x, du is negative dx. So this really is going to be negative du over u. So we know that's a natural log, and the negative in front, this will be the negative natural log of 1 minus x. You could go ahead and bring that minus 1 up there and make this the natural log of 1 over 1 minus x. Okay, but on the other side, let's just integrate this power series. So integrating the 1 goes to x goes to x squared over 2. Sorry, this should have been x squared. I just noticed that. So x squared goes to x cubed over 3. And so in the general term, this is going to be x to the k plus 1 over k plus 1. So let's just write this now in compact form. Now note, in the original power series, the constant 1 was associated with k equals 0. And now this x is associated with that same value, k equals 0. So we will start this at 0. And our general term is x to the k plus 1 over k plus 1. And that's the power series for the natural log of 1 over 1 minus x. So we're going to end today with this interesting problem. We want to find a power series representation for this inverse tangent function. Now, it's maybe not immediately obvious how we're going to do that, but what we're hoping we do recognize, or maybe that will help, is that this is either a derivative or an integral of something that we can easily build a power series for. And so that's what I want to talk through first, is thinking about derivatives and integrals. Do we know what inverse tangent of x is the derivative of, or do we know what it's the antiderivative of? The first thing you probably should think of is that we know what this is the antiderivative of, and that is, we know it's the integral of 1 over 1 plus x squared. And here we have something that we know from previous experience from Monday's lesson how to find the power series for. In fact, I'm going to refer you to the video we used on Monday and just say we already know what the power series for this is. Okay, so maybe just as a side note, we learned in a previous video that the function 1 over 1 plus x squared was represented by this power series right here. It was the one that went 1 minus x squared plus x to the 4th and minus x to the 6th. So it was an alternating series. The general term was negative 1 to the k times x to the 2k. So what I intend to do here is to find an inverse tangent power series. We will find the integral of the known power series for 1 over 1 plus x squared. And so let's switch colors now to yellow here. And so knowing this relationship, if I want to know the power series for inverse tan of x, we're going to get it by integrating the power series, and I'm just going to write the first few terms and then the general term. We're going to integrate the power series for 1 over 1 plus x squared. And I'll start off in the wrong way here. Let's make this a minus sign. So general term was negative 1 to the k, x to the 2k. So let's just write out the first few terms of this integral along with the general term. And I'm going to have x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7. So you notice in the previous one we had all even powers of x. Now with the integration we have all odd powers of x. So in the general term here, the coefficient negative 1 to the k, that won't change, right? That's a constant. But the variable x to the 2k is now going to be integrated by the power rule. So we bump the power up by 1. So instead of x to the 2k, it's 2k plus 1. And then we divide by 2k plus 1. And so this is our first few terms in general terms. So our conclusion might be that here we have the inverse tangent of x is expressed in this form. Here we go, and it's x to the 2k plus 1 over 2k plus 1. Now we're also instructed here to discuss the intervals of convergence. So let's do that for a minute. Remember that the power series 1 minus x squared plus x to the 4th, that is a geometric power series, and its interval of convergence is still that x is between 1 and negative 1. Now we did point out in the theorem today about derivatives and integrals that even though the radius of convergence doesn't change, the radius of convergence here is 1. But integrating and differentiation does often change the convergence at the endpoints. And so let's take a closer look at the endpoints of this one. If I were to investigate the left endpoint, -1, for example, I end up with this right here. My general term is now -1 to the k times -1 to the 2k plus 1 over 2k plus 1. Now, if I rearrange and look at that negative powers of -1 up there, you will, if you want to just even do it by trial and error, you'll notice that that does go back and forth between even powers and odd powers. So this is going to be an alternating series where, since the denominator will continue to increase, this is going to be a converging alternating series. And so I'm going to put an equal sign now on the left endpoint because that will cause us to have an alternating series that will converge. If I were to replace the x with a 1, it's going to do virtually the same thing, even easier to tell, because I'm going to get -1 to the k, and then, well, the x is a 1, so 1 to the power of anything is 1. I won't even have to write that, and it's over 2k plus 1. So this is definitely an alternating series with decreasing terms that go to 0. So I'm going to actually get convergence at the right endpoint too. This is the interval of convergence this time. All numbers from -1 to 1 inclusive this time. Now we have a little treat for you to finish this one off today. We have expressed the inverse tangent of x as a power series. And what we're actually going to do now is we're going to show you how we can express pi as a power series. So we're going to flip slides here, and we're going to take the result of this problem and do that now. So just stay tuned for a second here. So we just showed that the inverse tangent function has a power series that runs like this. We'll write the first few terms out again. Now, the challenge here is we're told we're going to express the number pi as the sum of an infinite series. Well, how are we going to use the fact that I know what the inverse tangent of x is, this power series right here? Well, note that in the previous slide, it was shown that the interval of convergence here is any number between -1 and +1, including those endpoints. And a very easy value of x to evaluate the inverse tangent at is in fact at 1. Okay, so if I were to evaluate inverse tan of 1, I would get this nice power series here. Just like this. Now we know that the inverse tangent of 1 is actually pi over 4. So I've so far can express pi over 4 as this series right here, this sum right here, infinite sum. So hopefully you see where this is going. If I just want to express pi as an infinite sum, all I've got to do is really just multiply both sides of this equal sign by 4 and arrive at this infinite sum right here. I encourage you to try this out on your calculator and see that it actually does get close to pi. Even with just the first few terms, you probably will be able to tell that we're going to converge to pi here. Interesting little fact here. Well, you've got a few more problems to try today on your assignment sheet, and feel free to email me some questions, whatever you're coming up with, and we'll see you back here on Friday.